Hello, today is June 6, 2024, and then today it is still about the electromagnetism, and then we are going to continue talking about the Gauss's law replication. Okay, so last time we're talking about the sphere. Actually, it's the conducting sphere where the charge is uniformly distributed over the surface. Remember last time we said we cut it right here, we looked it through this direction, that's what we see. But today, still the sphere, but the situation is a little bit different. So today what we have is what they call the uniformly distributed charge. What does that mean? Let's say this ball right here is an insulator, right? So whatever the charge, not only in the surface, but also inside the ball, it is also being trapped because it's insulated. They cannot move freely. So that we call it uniformly distributed within the volume of the given sphere. So even though you eyeball it, the problem seems pretty close to what we solved before, but indeed those are completely two different problems, right? Because the charge in this case is uniformly distributed everywhere. So let's say the charge is a Q and then the radius is R right here. Let's redraw this because I put a too many plus sign over there. It's hard to see. Okay. See, let's say that's the radius of R, and then the whole charge everywhere within the sphere is Q. Then we want to find the electrical field E in anywhere, which means if we draw a Gaussian plane, which indeed is something like that, and with radius of little r, and then we want to see what was the electrical field around this surface, right? And then we keep increase the r until r is equal to little r equal to big R, which is this sphere right here. And then we continue increase. So we're also talking about a case where the Gaussian plane is enclosed the given sphere. So let's say if little r less than big R. In that case, before we solve that, we need to figure out something. Let's say the charge density for the given sphere, called rho. Rho actually is the total charge divided by the volume of the sphere, which is that, right? And then for this little r right here, if we need to figure out the total amount of the charge contained in this sphere, then we just use the rho, because the charge is being uniformly distributed within the given sphere, right? So all we need to do is use Q I'm sorry, the QR means the Q, the total charge with the radius of R, that is equal to rho, which is the charge density, times the volume, which is little rq, right? And then we can plug in this in, and then the rho is right here. So we got a Q pi big RQ times pi little rq. So those cancel out. So what we have is Q little rq over big RQ. Now we have to use the Gaussian law. The Gaussian law told us the electrical flux is equal to E dot A, which is E equal to the Q enclosed over epsilon 0. So in this case, the Q enclosed is the QR we just calculated, right? So that would be big Q R cube, capital R cube, divided by epsilon 0, and then we can simplify this as Q R cube, epsilon 0 R cube. Now let's look at these two items. So since the electric field E at the surface of the sphere is always perpendicular, right? No matter which point you point to, it's always perpendicular to the surface, where the direction of the surface is also that way, right? It's also that way. In other words, the angle between E and A is 0. So the E dot A is equal to E, magnitude of E, magnitude of A, cosine. The angle between them is that, and then that indeed is EA, right? And then that equal to what? Based on the this calculation right here, that is QR cube, epsilon 0, big R cube. Now let's figure out the A. What is the A? A actually is the surface area of the little circle. So that is the E times 4 pi little r squared. That's the A. That is equal to QR cube, epsilon 0, big R cube. Now we can do some simplification, right? That's 4 pi r squared. My bad. So this cancel out, this just have r, right? And then 4 pi is going to be moved to here. So E actually equal to 4 pi epsilon 0 QR over R cubed. Again, if they ask for the direction of the E is just the radical direction, which means the direction of E is perpendicular to the surface. Now, if we increase this R, which means increase this R, then what about the value of the E? Since this is the Q, right, constant, this is constant, R is the radius of the sphere, is also a constant. So this is basically is equal to a big K. I shouldn't use the K because you might get confused. Let's say I put, what's later? Maybe so I can hardly think of the letter. Okay, what about big M? The M right here is going to be equal to everything right here times R. Look at this. this is actually the linear equation, right? So this is one variable, this is a constant equal to another variable. So if we draw a graph like that, let's say this is our R, this is the E, then we know, because this is the slope, right? So this is going to be a positive slope, like that. And then this point right here is when R, little r, equal to the big R, right? So when that happens, the E equal to Q, little r, in this case, equal to big R, 4 pi epsilon 0 R cubed. So that equal to Q, 4 pi epsilon 0 R squared. So that is the value of the E equal to Q 4 pi epsilon 0 R squared. Okay, so what if when R is greater than the little r, which means the Gaussian surface is somewhere around here? Then, again, based on Gaussian's law, the electric flux equal to E dot A equal to Q enclosed divided by epsilon 0. So the Q enclosed actually is equal to what? Equal to the total charge right here, which is Q epsilon 0. And then again, as what we discussed before, the surface direction and the electric field, they are in the same directions. So E dot A actually is E times A cosine 0 degree. That equal to Q or epsilon 0. This A right here actually is 4 pi R squared Q epsilon 0. So E is going to be equal to Q over 4 pi epsilon 0 R squared. Notice as the R increase, the whole value decrease. So the graph is look like that. Okay. So that's pretty much it I want to share with you guys today. Please, if you like the videos, please don't forget to subscribe it. It doesn't cost you any money, but it means a lot for me. Thank you so much. I'll see you guys next time. Bye-bye.